Welcome to Chapter 19 for Statistics, where we are talking about confidence intervals for proportions. Now, Garfield has a little bit of something to say about that. He's watching the news, and the weatherman says, taking a look at tomorrow's weather, the high temperature will be between 40 degrees below zero and 200 above. Garfield's smart. He says, this guy's never wrong. Well, this fits perfectly into what we're talking about right now, because our weatherman has provided us with a confidence interval. And Garfield's smart enough to realize that, dude, no kidding. Of course the temperature is going to be between negative 40 and 200 above. Unless you're like sitting in, I don't know, Siberia, you're going to be within that range. Now, we've been looking at a lot of different ways to structure data. We started off with categorical. We moved our way into quantitative. We talked about z-scores in the normal distribution. Well, all of the data that we've been talking about mostly focused on the idea of a population. Well, statistics is not about the true population averages. Statistics is about samples. And so it's a way of summarizing and presenting samples. What we're going to be talking about here is, all right, I've taken a sample, and what does that sample tell me about the world at large? What does this little piece of the picture tell me about the whole story? That's statistical inference. It is the primary focus of the class, and we're going to be talking about Frappy problems quite a lot, and the number 6 problem on the test is always some form of statistical inference, and it usually has multiple levels, and one of those levels is about confidence intervals. So what we're going to be talking about here is the fact that our best estimate of a population proportion, remember a population proportion is not something we always know, so we have to estimate it, and that estimation is centered around what my sample gave me. And that estimation, that just about between here and here, that is called our confidence interval. Remember, samples are not always perfect. In fact, some of them are going to be quite off. It depends upon how big the original population was and how big your sample was. So because samples are not perfect representations of the population, they're not perfect parameters, we create an interval with what we call a margin of error. It's kind of like a fudge zone. You know what, I think it's going to be here, but I'm going to be satisfied if it's within this area. So we're going to be looking specifically at what is a confidence interval, what's a margin of error, what is their purpose, and what affects them. And you're going to see that today, along with quite a bit of what we do in statistics, it comes down to very similar sounding words, and the questions sound very similar, but they ask very different things. We're going to have to pay very close attention to some of the stuff we're going over today. All right, so in a nutshell, a confidence interval starts with your estimate. Okay, this is huge. The confidence interval starts with your estimate, the statistic that you gathered from your sample. And it adds and subtracts to that what we call a margin of error. So I don't know if you watch the news very often, but the TV news guys always say the margin of error is plus or minus 4%. What does that mean? Okay, so if the TV news person says, I believe the high for today's weather is going to be 68 degrees with a 4-degree margin of error. Okay, they thought it was going to be 68 degrees. If it comes out and it turns out to be a high of 70, would you really consider them wrong? No, because it's within that plus or minus 4 range. It could actually end up being anything from 64 degrees to 72 degrees. Because he believes that the true proportion, he says, you know what, I think the weather's going to be here, but whatever it really is should be within 4% of his estimate, with some probability, with some degree of certainty. And the degree of certainty we're going to talk about in a little bit, and that's crucial. And a bigger degree of certainty typically means a bigger window, just like what Garfield saw. Your weatherman is going to be 100% certain if you believe that the temperature of the earth is going to be somewhere between a firing inferno and a ball of ice. Yeah, you kind of expect that to happen. Now this is huge. I'm switching a word here. This says the confidence level. The confidence level tells us how likely it is that the method we are using will produce an interval, this guy up here, that contains the true population parameter if we use it many, many times. Okay, this is very important. A confidence level is talking about if I were to do multiple samples, how likely is it that each of my samples will contain the true parameter, the true proportion, the true mean. So the confidence level does not tell us the chance that a particular confidence interval captures the population parameter. It doesn't say that if, and for example, we'll say a 95% confidence level. It does not say that there's a 95% chance that I'm going to be right. What it says is if I do this interval, if I do this sampling method 100 times, 95 of those should contain the true parameter. And I know that sounds like it's splitting hairs, but hello, welcome to statistics. So the confidence interval gives us a set, a range of plausible values of things that would work for a specific parameter. And remember, a parameter is the true measure of the population. This is giving me the statistic that I calculate, an interval for that we hope captures the true population parameter. All right, now everything we do, we're going to be coming back to assumptions and conditions over and over and over again. Now, these are all going to be very familiar. We talked about these in the last chapter. So we can check to see if an assumption is plausible, if I can even go forward and apply this work by checking some conditions. Now remember, we had our independence assumptions because we had two. We had independence and we had sample size. In order to meet the independence assumption, we have to be able to say plausible independence condition. I believe that the data values do not affect each other. So when we answer this question, you have to think to yourself, is there any reason to believe the data values affect one another? Guys, guess what? When we're talking about weather, one day is not independent of the other. One day's weather patterns and what we see is greatly affected by what happened the previous day. The randomization condition still applies. We have to be told that the data was sampled randomly, or they have to say that it was a randomized experiment. If they don't come out and say these things, we could have trouble. We might just need to say that the assumptions and conditions were not met, proceed with caution, but this is a very big piece to this. Also our 10% condition, remember this is our not too big condition. If we're drawing without replacement, to make sure that one does not affect another, we can't be more than 10% of the population. And on the other side of that, the big enough assumption, sample size assumption, do we have at least 10 successes and failures? And remember, if we take that back, that means that NP has got to be greater than 10 and NQ has got to be greater than 10. Where P is the chance of success, Q is the chance of failure. All right. When we're talking about our sampling distribution versus a confidence interval, remember the fact that a sampling distribution, if we met all of my assumptions and conditions, which have not changed, then that means that the sample follows a normal curve. And we believe that from the sample, it is centered at the proportion with a standard deviation of root PQ over N. So it's very dependent. My variance, the amount that my results can change is centered around the sample size itself. but it's centered at a probability with this standard deviation. And I want to make sure that you understand something here. This is very, very important. P here with this notation means that we're talking about our samples, not the true population. There's a difference. You see this guy right here doesn't have a little hat above it. That is because they mean two different things. When I'm talking about a P with that little hat or that caret over it, that means your sample probability. This guy means your population probability. This is what it actually is, or what we actually believe it to be. This is what I got from my sample. And when we're talking about the distribution of these, we go back to our normal model being unimodal and roughly symmetric. We center it here. This is the sampling distribution. Sampling distribution, we believe it to be centered at P with a standard deviation of root PQ over N. So it's highly dependent upon the sample size. And we expect 68% of my samples to fall within 1 standard deviation, 95 within 2, and 99.7 within 3. But please remember, all of those percentages are estimates. The actual the actual standard deviation for where we see 68% we're going to talk about in a little bit. And what's going to happen is usually we're going to have a sample proportion. I'm going to take a sample of bags of chips, and the probability that that bag of chip actually contains the right amount of chips. Or I'm going to look at my class and say, what is the probability that a student gets an A in my class? This is what's based off of my sample. When we have a sample, we have to work backwards to where we think the actual population proportion is. Now this is huge. Sampling variability, the fact that my samples will change from one to the other, we cannot be certain that our sample statistic matches the population parameter. It was a guess. And so we have to talk about how certain we are about my guess. How confident am I in my guess? And to do that, we use a confidence level. Now our confidence levels really depend upon what the situation is. If lives are at stake, if I'm wrong giving somebody this drug and somebody dies, I want a really, really high confidence level because I want to make sure that we don't have any of those crazy side effects. If I want to be confident that in each area we actually get a certain amount of snow, you know, that's got a little bit more wiggle room. Lives aren't going to be as at stake if I'm off by a half an inch with my snow predictions. So they will vary all over the place. They can be as small in what we call the soft sciences as 60%, or they could be as strict as in some of my harder sciences, my medical, my engineering, as 99% confidence or even higher. Our most common confidence level is 95%. And this is something I want you guys to just kind of make a little bit note of, because if I do not tell you what the confidence level is for a specific problem, go ahead and use 95%. We do a lot of assumptions in statistics, so if it is not stated to you, assume your confidence level is 95%. Otherwise, we get to have way too many, we get variation within our own answers. Now, this is kind of the cool part. This is my sampling distribution of whatever my statistic is. It's centered at the mean, it has standard deviations, and these are all of the values that are possible of my statistic. And these guys down here show me what different samples resulted in. Some of my samples had averages that were extremely close to the true average. Some of them were really, really far off. Our confidence level decides how many of our confidence intervals will contain the true population parameter. Okay, now this is very, very important. You're going to see this verbiage, this language used all the time. A level of confidence. When we are asked to interpret a level of confidence, not the confidence interval, but the level of confidence, or the confidence level. What we're going to say is we're going to say that after repeated samples, some percent of the samples, whatever we're believing our confidence level to be, will contain the true parameter between whatever the values are. Okay, so this is a really cool program here that's going to allow us to simulate a confidence interval. Now, I'm going to look at the confidence interval based off of proportions. Now, it's called a binomial distribution simply because you have two choices. You have a success or a failure. Bi means two, binomial distribution. We have two choices. Don't worry about this guy. This is just, there are different types of methods that we can use to find this. We are never going to deal with that. So this symbol right here is just a strange notation for saying not pi, but this is where my chance of success is. And we're going to leave it at 50 because a 50-50 chance, this allows us to center our graph fairly nicely. N means my sample size, and how many intervals am I going to create, how many samples am I going to take, and therefore how many intervals am I going to create off of that, is 30. And I want a 95% confidence level. So let's see what happens. This black line here shows me what the true P is, what the true probability of success is, and that is at 0.5 because I set this. Now, depending upon how big my sample is, my confidence interval is going to be at a different width because my confidence interval, you'll see, is based off of my sample size. And here I have done 30 different intervals. So I've taken 30 separate samples, and for each of my samples, here's the distribution of their proportions. You'll see that most of these are in green because most of these samples fell within a reasonable range to capture the true proportion. All of these intervals, these were the means of all of those intervals, they all captured the true proportion, even though the true proportion is right here. And look, there's a massive gap right there. But I have two that are off. So out of my 30 intervals, 28 captured the two intervals, 28 captured the true mean, so I have a success here of 93.3%. If I do another one, I did another 30, this time only one of them fell out, so my running total is getting closer. Let's do another one. Ooh, that was a good one. We got everybody. But you can see as I go through here, the more samples I do, sometimes I'm really, really good, and all of my samples capture the true population proportion. But some of my samples are off. That's natural sampling variability. I'm going to have some bad samples. So even though this sample right here also has a 95% confidence level, it's a sample that just didn't actually work out. All of these samples are possible following the exact same techniques. Most of them capture the true population parameter, but not all of them do. See, for these we've got a lot of really good ones. We have a couple that are just on the verge of not quite making it. And the more I do here, you're going to see that my running total, my actual number or percentage of intervals that capture the true population average is going to get closer and closer to 95%. So if I up this, let's up this to 50 and see what happens. So I'm now taking more intervals. More intervals. So sometimes I'm really good. Ooh, sometimes I'm really bad. But in reality, whenever we do a confidence interval, we do one at a time. Another one, and another one. And so we might not see how my confidence interval can or cannot capture it. We might think that, oh, that this captures 95% of the data, but it doesn't. What this means is that out of repeated samples, 95% of my samples will be good. It doesn't mean they all will. You can see as I go through these, some of these get really, really close to not working, but we've been fairly successful so far. I also want to show you what happens if I change my sample size. Okay, so let's see here. This was a sample size of 20, and we finally have one that doesn't work and one that does. If I change that sample size and I make it bigger, what should happen to the confidence interval? I'm doubling the sample size. It makes this interval smaller. So go back to a sample size of 20. Take a look at what it looks like. If I do that 4 times as large, let's go to a sample size of 80. Hopefully you guys should know that it's related to the square root of the sample size. So 4 times larger, square root of that should be half the size. My sample size is directly related to the size of the sample. I'm sorry, our confidence interval is related to the size of the sample. All right, let's go back to what we were talking about. So let's think about what a confidence interval means. If we take the 95% confidence level, and this is our standard, it says that there's a 95% chance that P is no more than, and please understand this is an approximation, is no more than 2 standard deviations from the sample proportion. The true proportion in a 95% confidence level should be no more than about 2 standard deviations away from my sample proportion. So that means if we reach out 2 standard errors, and that's my margin of error, not standard deviations, but standard errors, because remember standard deviation, standard error are slightly different. Standard deviation is root PQ, standard error is root PQ over N. If we reach out 2, we are 95% sure that P will be in that interval. Whatever direction it means, we are 95% confident that that interval contains the true proportion. That is the confidence interval. So the way that we interpret a confidence interval versus a confidence level, a confidence interval says that there is a 95%, we are 95% confident that the interval, whatever the interval that we have, contains the true population proportion, or the true parameter. Our confidence is in the process of constructing the interval, not any one interval itself, because we've seen that some intervals fail. It's not about the interval itself, it's about the process that we go through, and if we were to repeat that process over and over and over again, 95% of those resulting intervals should contain the true population parameter. So we have 2 different things here. If I'm going to interpret a confidence interval, then that means that we are 95% confident that that interval, whatever it is, contains the true proportion. If we wanted to talk about a confidence level, we would say that we would expect 95% of all 95% confidence intervals to contain the true parameter that we're trying to estimate. So if I were to do it over and over and over again with that specific level, 95% of them should capture the true parameter. But you got to be careful, because two standard deviations is an estimate of where 95% actually is. We try to use estimates as little as possible. So instead, to be as accurate, we need to calculate the critical value, which is the z-score that goes directly with a 95% confidence interval. So how is this done? This is very, very important. To calculate a 95% confidence level, to calculate a 95% confidence level, or really any confidence level, you have to be aware that all of my confidence levels are centered about the mean, wherever we believe this to be. And for a true normal distribution, there is an area of 1 under the whole curve. So this guy right here, the halfway point, is at my 0.5. It doesn't matter what my P is. We're talking about the normal curve in general. And when we estimate a 95% confidence level, it's about going out 2 standard deviations because I want to capture 95% of the data. But in order to do that, I have to find the z-score that either matches to either one of those points. This is my negative z-score, and this is my positive z-score. So think back, if I give you a probability and you want to find the z-score, what command do you use? Well, let's take a look at the calculator. We know it's going to be in the second vars, and it's going to be one of these guys. When you have a probability and want to find the z-score, you're going to use the inverse norm. And this here is actually the setup, and that is because to find the z-score that corresponds to 95% confidence interval, this 95% block is broken up into 2 pieces. Half of it goes this way, half of it goes that way. So half of 95% goes up from 0.5, half of 95% goes down from 0.5. So the way that we can denote this in our calculator is by saying the inverse norm, and when we talk about the probability, since it's centered at 0.5, I always start with 0.5, and you know, just for giggles, to keep it positive, I use the plus instead of the minus. Whatever this number here is, whatever my confidence level is, so 0.95 over 2, with a standard deviation of 0, with a mean of 0 and a standard deviation of 1, because we're just following the normal model here. So I'm going to go to my calculator, mean of 0, standard deviation of 1. If you are working on an older calculator, this is exactly the way your screen should look, although you will actually see the inverse normal command. There it is. And there it is. And we're going to round that to 2 decimals, 1.96. And you're going to see these numbers so often that they are going to become ingrained in your brain. So if I were to do this again, but with a 98% confidence interval, the 98 changes spots here. So I'm going to do inverse norm of 0.5 plus 0.98 over 2, because remember we're talking probabilities, comma, 0 and 1. And so I'm going to go back to my calculator. Inverse norm, and just tap over that and make it an 8. And if I were to do a 98% confidence interval, I'd use the number 2.33. So to calculate, like just extrapolating upon that, to calculate any confidence interval, any of my standard errors, I need to use an inverse normal of 0.5 plus whatever your percent is written as a decimal over 2 based off of the normal model, so a mean of 0 and a standard deviation of 1. So once we've gone through and we've figured out what the z-score is that matches with whatever the probability or the confidence level that I'm trying to find, in order to finish it off, you have to understand that the margin of error itself is the critical value, and this right up here, what we found were the critical values, times the standard deviation. Okay? So it's very important that you understand that. Let's add a little bit of editing here. So if you understand that the margin of error is the z-score times the standard deviation, that should help you understand the fact that to find the confidence interval, just a little bit of throwback to what we talked about in the beginning, the confidence interval is found by taking your estimate plus or minus the margin of error. So that means the confidence interval is centered at your estimate plus or minus the z-score, the critical value, not the approximation, times the standard deviation. So we've talked about the sampling statistic, the probability that comes from the sample. We've talked about how to find the z-score. So the very last piece is that standard deviation. The thing that you have to understand that we're dealing here with a sample, we don't actually know what the standard deviation is. We do know that for a sampling distribution, the standard deviation of the sample is root PQ over n, or it's sigma over n, because the population distribution, or the parameter, is root PQ and sigma. And so when I'm going from the parameter to the sampling distribution, we take the truth and we divide it by the sample size, and it's all under the square root. But the problem is here is, remember, we don't know what the true population parameter is. We don't know the proportion. We don't know the mean. We don't know these things. But that doesn't mean that we're stuck. So instead, we use the sample statistics to estimate the population parameter. So what you're going to be doing is we're going to be using what's called the standard error instead of a standard deviation. The standard error is slightly different because it uses p hat, q hat, and s. So this means the standard error uses the sampling's probability of success and failure, or the sample's standard deviation, and divides by the square root of n. So putting all of that together means that whenever we're trying to find a confidence interval, the formula for the confidence interval, this is extremely important, and the symbols here are crucial. Just P talks about the population proportion. We don't know the population, we know the sample. Plus or minus the critical value of my z-score, whatever matches to my confidence interval, times, and since we don't know the standard deviation of the population, we take the standard error. And so for a proportion, which is what we're focusing on for this unit, my confidence interval is the observed proportion plus or minus the z-score for that level times root p hat q hat over n. And remember, we've had a lot of different things that we've talked about. We've said primarily here that a confidence level is saying if I repeat the process over and over and over again, I believe that a certain proportion, a certain probability, 95% of my resulting confidence intervals will contain the true proportion. Again, a confidence level of 95% says that with repeated samples, 95% of the resulting confidence intervals should contain the true population parameter. Whereas a confidence interval says that we are 95% confident that the true population parameter falls within a specific interval, whatever it is that we calculate. And we're actually going to be doing those calculations in class. So I hope you guys have put together a list of questions or things that you're not quite certain with, but I really believe that when we start working through problems in class, a lot of this will fit into place. You know what? If not, we're going to be spending a couple days on it. All right, see you all in class. I hope you have a good one.